Hey, Advanced Calc students, we are doing the Chapter 7 ice sheet, starting with 7.1. Like I said before, this is probably the hardest chapter. You really need to read this first section very carefully and go through it piece by piece because there's a lot of new definitions and a lot of kind of subtlety to integration. So this section is huge, and if you don't understand this section, please tell me because then you won't understand the second or third one either. There are 6 problems on the ice sheet. We'll see if we have time to do them all. But the first 2 are the true-false, which I think are pretty important to go through. So I'm not going to write the problems on here, but I'll state them. So there's A, B, and C for 1 and 2, some true-false statements. And then 1A is about whether the upper sums and lower sums are a bounded set, and that is true because if you have any lower sum, it's going to be less than or equal to some upper sum, but no matter what the partition is, this is actually a problem I give you guys for the integral in Calc 1 or Calc 2 that you can use the extreme value theorem and kind of, if you have an integral, which should be in between these, it fits inside kind of a box. So here's the big box, and then here's the little box. And so the idea is that there's always a kind of a max value that if it's inside this big rectangle and then it's above this little rectangle. So that means that no matter what the partition is, if you take all the partitions, they all fit in here. So that means if you take all the partitions and all the upper sums and lower sums, you get this bounded set. Here's the upper bound, and here's the lower bound. So that is true, and that comment I think is right before definition 7.1.3 in this section. Okay, the next question is if you have P and Q, excuse me, if they are both partitions of AB. We're not necessarily dividing it equally, that's what we mean by partitions, just we've cut up the set. Then P union Q is a refinement, or I'll say refines both P and Q. That's true simply because refinement means that the new thing is a superset of the old thing, and that is just a justifications fact that P and Q are both subsets of the union. So not much to do there. So that one's true, that one's true. And then this one is all about nomenclature. Like I said, studying this section carefully and making sure you understand which word is which is important. This one says F is Riemann integrable if and only if its upper sums and lower sums are equal. That should feel true, but it's false because the sentence is a function F is Riemann integrable if and only if its upper integral, not sum, and lower integral are equal. So in this book, they tie the word upper sum and lower sum to unique partitions, and then among other partitions, you take the upper integrals and you take the upper sums. That was exactly my point about being careful. Take the upper sums and then take the inf of that. That's what they call the upper integral. So this is the inf of the upper sums. And then that's unique, and then the sup of the lower sums, that's unique, that's the lower integral. Those are what have to be equal. It's really, the way the sentence is worded on the true-false, it says its upper sums and lower sums are equal. That's kind of ambiguous anyway, because upper sum and lower sum are always attached to a partition, whereas the upper integral and lower integral are not. They're tied to the set you're integrating over. So, upper integral, lower integral, that's what they call these inf and sup. So that sentence feels like it should be true, but it's false. Okay, let's go to 2. So 2a says when an integral exists, it is a unique number that lies between L, FP, and UFP for all partitions. So they're saying if this value exists, it's the unique number between these for all partitions P of AB. This is 2a. then this is true. This is pretty much the definition of the integral. Remember that we just said that it's if the upper sum and lower sum are equal. Well, if this number is in between here every time, then if you take the sup on this side and the inf on this side, then you get the upper integral and the lower integral. And if those are equal, then this is the number each time between them. So that's kind of equivalent to what we just talked about on 1c. So that's true. Okay, 2b says that if P and Q are partitions of AB, and F is bounded on AB as part of it at the beginning of the problem, then any lower sum on any partition should be less than any upper sum on any other partition. My first impulse is to prove this wrong and say, hey, if I take a wide enough partition and make this thing fat and make that one small, somehow this should fail. However, you always have that the lower integral is less than or equal to the upper integral, and any lower sum, remember that this thing is a sup, so that would be below this, and that this thing is an inf, so this would be below any upper sum. So if you believe all of those things, then this is true. So this problem is true. Okay, and the last true-false question here says f is integrable on a to b, then given any epsilon, there's a partition P, so f is integrable. Such that a lower sum is greater than the upper integral minus epsilon. Okay, so this is coming from, if you're not sure about this true false, if you just go look through the problems, or through the text and the definitions and problems and whatnot, and theorems, there's a theorem that has an epsilon in it, there's only one. And it says that u of fp minus L of fp, that difference is going to be less than epsilon. So let's rearrange to match this problem by moving epsilon over here, and L of fp over here. And so this is close to what the problem says right now, but we have u of fp, they have u of f. Remember that u of f just above here is an inf of all the u of fp's. So if I take an inf here, that would be even less. And so now if you look at these two, you have the inequality that you were trying to get up here. So all three of these are true. Tricky, tricky. Okay, so those are the first two, the true, false. And all of those are worth going through carefully because all those are just making sure you understand those definitions. Okay, so 3 is a great example of trying to understand what L of fp and u of fp do. And I think, I'll have to check in a minute, but I think number 4 is a sign. So this would be a good one to look at because it's very similar to the one on your assignment. So we've got f of x is x squared, and we've got an interval 1/2 to 3, they use 0.5. And first they use partitions. So they're using the points where the partition kind of breaks. So they don't go evenly, they go 0.5, 1, 2, 3. And then they say for part B, do it again. And now go every 0.5. So this is A. 0.5, 1, 1.5, 2, 2, 2.5, 3. And then C is to use calculus to actually do this answer and see how close you get. Okay, so these are not super fun, and they're kind of tedious, but they're important to do. Okay, I may only do part A, we'll see. So let's do the lower sum first. What you're going to do is in each interval, so each chunk from here to here, here to here, here to here, you're going to, for lower sum, you're going to use the smaller number. And that's not necessarily left hand or right hand, but it is in this case because x squared is increasing, right, on this side. So I'm always going to use the left-hand number because I want the lower value for a lower sum. So we're not thinking left hand and right hand, we're thinking lower and upper. So that's a little different than the way you thought about this in Calc 1. Okay, so I want to take 0.5 squared, that's the y value, I plug in x, so it's this left side. And then the width of that first chunk right here is 0.5. And then I want to take 1 squared, and the chunk from 1 to 2 has width 1. And then I want to take 2 squared, and the width from 2 to 3 is 1. So we get 4, 5, and then I don't know 0.5 cubed. So that's 0.125. So 5.125 is my lower sum. Okay, so for my upper sum, I'm now going to use, because this function goes up to the right, I'm going to use the right hand for each of these intervals. So same idea, but I'm changing the values. I'm using 1, 2, and 3. So 1 squared, and then width of 0.5 for that first region, 2 squared, width of 1, 3 squared, width of 1. So that should be 13.5, I believe. Yes. Okay. Sorry, that's not B. That's still part A. Part A has 2 parts, so you know the integral is at least this big and no more than this big. Now, when you do part B, these should get closer together. I'm going to encourage you to do that part yourself because this video is already running long. But for the lower sum, so now you have 0.5 width each time, and you're going to use, again, because it's an increasing function, you're going to use the left-hand side, and then for upper, use the right-hand side. You should get 6.875, so that went up, which makes sense. And then the upper sum should come down, and you should get 11.25. So please do that on your own and make sure you get that, because I'm pretty sure a problem like this is on your exam as well as on your homework. And then C says just do the integral the old-fashioned way, x cubed over 3, plug in 0.5. This answer should be between these. So you get 9 minus 0.125 over 3, which is 8 something. About 8.96, which was between these. So that's a logical answer. All right, so that's number 3. Okay, number 8 is to give an example of a function that is not integrable, but x squared is integrable on 0 to 1. So f 0 to 1 is not integrable, but f squared from 0 to 1 is. Okay, I believe this is in the section. If not, you should already be very familiar with the Dirichlet function. I'll call it D, and we'll fix it here in a minute. This is a key to integration, and those of you taking real analysis, we're going to use this function quite a bit to make some key points. This is the guy that's 1 on the rationals and 0 on the irrationals. I guess we'll stick with 0, 1 since we're using 0, 1 for the domain. This guy, his upper sums are all 1, his lower sums are all 0, so this guy is never Riemann integrable. So if I square this guy, he would be the same, wouldn't change. 1 squared is 1, 0 squared is 0. But let's modify it. Let's use this function. If I do this, I still fail to be Riemann integrable because all my upper sums are 1 and all my lower sums are negative 1. But now if you square that, 1 squared is 1, but negative 1 squared is also 1. So f squared would be identically 1 on 0, 1. And that's integrable, that has area 1. So in general, it's good for different topics to have a key sort of like bag of tricks for your classic counterexamples. For integration, it's almost always the Dirichlet function. All right, so for number 9, it says prove or give a counterexample. So maybe it's true, maybe it's false. If f and g are integrable on a to b, and h is in between them, then h is also integrable. So f, g, integral on a to b, f of x less than h of x less than g of x on a to b, and then h is integral. I think I just gave you the answer, and I'll prove my point again with the Dirichlet function. Just take 0, 1, and take f to be identically 0, and g to be identically 1, and h of x to be the Dirichlet function, the one we just had a minute ago. So f is always 0, which is integrable. The Dirichlet function, remember, is 0 on 0, 1 intersect q, and then, 1 there. You can flip it around, but let's stick with what we had. And then on the irrationals, it was 0. So that's always 0 or 1, so it's bigger than that, and it's less than or equal to something that's always 1. The constants are easily integrable, and h of x is not integrable. So again, to make my point, the Dirichlet function, he's your guy. So this is false. There's my counterexample. Alright, one more for 7.1. This is number 12. It says let f be a bounded function and suppose that f is non-negative in that whole closed interval. Show that the lower sum is greater than or equal to 0. So f is bounded on a to b. F is greater than or equal to 0 on a to b. Show that L of f is greater than or equal to 0. Okay, so let's talk about partitions first, because L of f is the soup of all the partitions. So if you take the partitions, these were the sum of the mi xi's, or maybe these are called delta xi's, the width of each interval, and you were summing this. Remember that the mi is the inf in this little slice of the partition. They might use -1 and I -1 and I, but it doesn't matter which way you're going. You got some sort of chunk of an interval, and you're taking the inf. These are function values, and then the x value is coming from this width. So this is the height, this is the width of those little rectangles. But f of xi is greater than or equal to 0 for all I. So that means that the mi's are greater than or equal to 0 for all I. And the delta is always positive, so each of these is greater than or equal to 0 for all I, which makes the sum greater than or equal to 0 for all I. And then LF is in soup of these, so it's greater than or equal to these. So that's all you need. That's really not a hard proof, but it's a lot of grinding through individual definitions. So really making sure you have down how to do these mi's and xi's, maybe going back to problem 3 and 4, making sure you understand what's happening. That's all key. All right, that's it for the 7.1 ice sheet.